to start to understand the chemistry, we have to now get into periodic trends. And with periodic trends, there's four of them, five. We have first this idea of effective nuclear charge. We have atomic size. We have ionization energy. We have electron affinity. And we have metallic character. We could also say electronegativity. But we already discussed this idea. Oops. And we'll reinforce it a little bit here as well. So the first stage here is to look at effective nuclear charge. So the first thing that we have to understand is that the nucleus is positive. I hope we all know that. Or it's positively charged. That's equal to its nuclear charge, right? The number of protons. Right? Remember, protons are positive. So, that's one of the reasons, right, that the electrons are hanging out, right? Is that the electrons are hanging out because they have a Coulombic attraction because they're negative to the positive core. And then we just got through all the orbitals to explain how those electrons are distributed so that they don't repel one another because of that negative charge. But here now we're just talking about this idea of, what's holding the electrons in terms of chemistry, right? And I think that's where we're going here as far as the chemistry of these elements. So the nucleus is positively charged. That's what nuclear charge is. Effective nuclear charge is, basically what is felt, or this, Coulombic attraction by the valence electrons. So we have this notion of charge, nuclear charge, which would be just the number of protons, but then there's this notion of effective nuclear charge. And that's what's felt by the actual valence electrons. This is basically what is either, holding. Let's say that another way. We could say this is what, is holding the valence electrons, to the atom. Also, it could be viewed as, an attractive force to get more electrons. So it's just this. It's really this attractive force, and so we could think about it. And I don't know if this analogy is going to work, but I'm going to try. Is that we have this very nice clearing, and I'm trying to put this into perspective of like taking a hike in the woods. When you walk in the woods and you hike on trails, every now and then you come upon a clearing, right? And so that's what I'm talking about here. We come across a clearing, and we could say that this is, the nucleus with that, positive charge. And then if we were to consider, walking through the woods, well, we would have, trees, which I'm trying to represent. I don't know if red is the best color here. But we have all of these trees that are surrounding the clearing. And we could call that maybe something a little bit more specific. We call these really core trees or core electrons in terms of the analogy. So these core electrons, right, are hanging out about the nucleus because of that positive-negative Coulombic attraction. If I'm an electron out here, and we could call that a hiker. That's the valence hiker, or the valence electron. Our nucleus, right, which is something that is positive because of the protons, right, has Z. And that's the symbol for the atomic number. So we have a certain number of protons, and these electrons are feeling an attractive force to that core. To different degrees. These are all core electrons. Right, that's the Coulombic attraction. Between the nucleus and the core electrons. Now, if we look out to our far liar, right, the hiker, right, the hiker can't see the clearing. I don't know, maybe a little. But it's it's not clear till the hiker would get closer. To the clearing. So we have an attractive force out here. Right? It's an attractive force It's a Coulombic attraction. But it is much weaker since there's so many electrons or trees that are in between. So I don't know if that analogy works for you. Maybe it doesn't. I apologize if it doesn't. But basically what I'm trying to say is that there's a force of attraction that exists between the positive core and the negative electron. The closer you are to that, as far as if you are an electron, the closer you are to the positive core, right, the more of that atomic number you feel, right, as far as the number of protons that are there. If you are way out, in terms of very distant and now in the valence shell of electrons, well, there's a lot of stuff that's in the way, right? There's all these core electrons that are in the way. And the core electrons are hiding the full positive charge that the nucleus actually has. So basically when we get into now Z effective or effective nuclear charge, right, is the, attractive force, from the nucleus to the valence shell. And it's really an equation where you have here our effective nuclear charge here we have our atomic number, number of protons, and then we have S, which stands for shielding electrons, but really these are core electrons. So Z effective is kind of this like outward charge, positive charge that electrons feel on the very most outer regions of the atom. And so that's what's now describing whether we want to lose electrons or gain electrons in terms of the chemistry. If we have an understanding of Z effective and how that works in, that Coulombic attraction holding the electrons to, the atom, to the nucleus, now we can start to consider why things want to lose electrons or things want to gain electrons. And so that's the relevance that we'll start to see here with Z effective. First, let's do an example of just the calculation with Z effective. So we want to calculate the Z effective for oxygen. And if we bring back our periodic table, we have here our oxygen atom. And if we look at essentially its Z is equal to 8. Right, that's its atomic number. So oxygen has this Z value equal to 8. Now we have to figure out its core electrons. And if we look at oxygen, that would be, let's do the noble gas shorthand. That would be helium, and then 2s2, 2p4. So here is our core electrons, which is really just 1s2. So S here is equal to 2 as far as our shielding electrons. And we're just solving for Z effective by plugging in those two values. So our Z effective would be equal to our atomic number, which is atomic number 8, minus our shielding electrons, which is 2, which gives us a value of plus 6 for the Z effective. Let's try that one more time. Let's calculate Z effective for magnesium. So if we bring back the periodic table again, now we are over on the left side with magnesium. So if we look at its atomic number, right, Z is equal to 12 in this case for the magnesium. If we go to the core electrons, right, magnesium has neon as the core set, and then it would be 3s2 for its electronic configuration. So we have 1s2, 2s2, 2p6, or 10 core electrons. So now, plugging it into our equation, we can find that we have what atomic number of 12 minus 10 core electrons, and we have a Z effective of plus 2. So we can calculate this notion of Z effective, right? And again, this idea is, really what is the outermost electrons feeling in terms of the positive core? There's a lot of interference with the core electrons, and so that's what we're looking at with this idea of Z effective, is what are they feeling on the very most outer reaches of the atom. Periodic table also has Z effective worked into it. And it just so happens that Z effective is also the number of valence electrons. When we're talking about a neutral, element. And our group number again. So there's that relationship that we had between valence electrons and group number. We also have that now between Z effective and group number. So if we were to bring back the periodic table and show you this again. Oops. Remember, we have these group numbers of 1A and 2A, and then we had 3, 4, 5, 6, and 7A. We also had the B's. Right, in terms of the group numbers. And so if we were to look at now this idea of let's say arsenic. Arsenic. It's right here on the periodic table. Right, arsenic has 33 electrons. We would represent it like this in terms of our electronic configuration. And I can immediately say, from, the group number equal to 5A, I can say two things. I can say arsenic has 5 valence electrons. And they're right here, the 4s and the 4p. Remember, the 3d is full, and now that's part of the core. Right? I can also then say that arsenic has a Z effective equal to +5. Let's check that out. So we had our Z effective, which is our atomic number of 33, minus our core electrons. Our core electrons would be our argon, which if we go up to the top, scrolling up a little bit here, argon would be 18. But then remember, we have the 3D, which is 10, so there's 28. And that gives me +5. So here is our Z, and here is our core, which was the argon and the 3D10 to come to that value. So that's the idea of Z effective, is that we can basically calculate it, but we can look at the group numbers to also just really figure that out pretty quickly. So there is a trend in terms of Z effective then. We've already sort of talked about it in this light, going from left to right. Z effective increases. Right, and that was by the kind of that group number idea of 1, 2, 3, 4, etc. But we also have, a vertical relationship as well. And the problem with the vertical relationship is that, if we were to calculate it, we would get the same actual answer. For instance, hydrogen, lithium, sodium, potassium, rubidium. I'm looking at the far left portion of the table. They're all in that group 1A, so they all, when you calculate it, would all have a Z effective of +1. But we do find that, Z effective increases in this manner. And it does so because, there's essentially less core electrons, and so you really are physically getting closer to the actual nucleus. So this is the trend that we see, but you can actually calculate it as well. So that's Z effective, and I think the biggest thing that we have to take home from this is, the greater the Z effective, the greater the attraction to gain electrons and reach that noble gas electronic configuration. Remember, we were talking about before things that want to gain electrons, things that want to lose electrons, right? Right, we have things that like to gain electrons because we have a high Z effective, or, a large Z effective. And then if we go to the other side of the things, right, where we now like to lose electrons, that's because we actually have a low Z effective, or a small Z effective. So in much the same, now we're trying to lose them to get to that noble gas electronic configuration. So again, I'll scroll back down in a sec, but again, this is the goal that we have off to the left. All right? Right? That's the goal that they want to get to. Some like to lose, some like to gain. And Z effective helps to describe that. If you have a high Z effective, well, then you like to gain electrons because you actually have this great outer sheen of positive charge, and that's an attractive force to electrons coming your way. While if your Z effective is really small, well, then it's actually, you don't have as much of a hold on those electrons, and it's just a little bit easier to let them go to get to the same level, right? They're both trying to get to, the goal. They're trying to get to that noble gas electronic configuration. But Z effective now also is another way to visualize that in terms of ones that want to gain and ones that want to lose, is really this reflection on what their Z effective is and how large it is or how small it actually is. The second trend is atomic size. And so atomic size basically has a trend of, decreases from left to right and from bottom to top. So if we have our present periodic table here, now drawing this trend, we're talking about Z effect. I'm sorry, apologies. We're talking about atomic size decreases from left to right. And we also find that atomic size decreases from bottom to top. So that's the trend that we see with atomic size, and it's really related to, again, that notion of Z effective. So if we're going from left to right, Z effective is increasing. So the electrons are, held tighter and closer. So, Z effective, is really increasing along with that type of decrease that we see. And we see the same with, the notion of from bottom to top. So there's that relationship again with that hold on electrons. In going from, bottom to top, still the same idea with Z effective. But also realize you are going down in principal quantum level. So you have less shells, of these electrons. So that's another way to view it in going from, the bottom to the top, but not so much with left to right. So Z effective is a good way to describe the trend that we see. And just to scroll back up again, right, we see atomic size decreasing going from bottom to top and from left to right. So if we were to compare, as an example here, magnesium versus oxygen, and ask the question, which is bigger, right? We just need to go to the periodic table and look at the relationship of where we find those two species, right? We can see that our magnesium is off to the left. We have our oxygen over to the right, right? The magnesium is further to the left, and further down on the periodic table. So it is bigger. So magnesium is the bigger element. So that's just how you compare that notion of, the trends. Again, realizing that, we're talking about, atomic radius, where we would have, radius decreasing. Right, in terms of that trend. What about what I would call the Catty Corner relationship? And it's like a regional thing, right? In East Coast it's called soda, Midwest it's called pop. We have Catty Corner, we have Kitty Corner. There's certain ways. You have sub, we have a hoagie. We have different ways of describing things depending on our region. And so Catty Corner is basically a relationship that looks like this. Where you have the corners touching. So let's do an example and try to highlight this. So let's look at which is the largest element. And we have carbon, phosphorus, nitrogen, or oxygen. So if we go to our table, and I think that's always a good idea, is get the periodic table out. Take a look at the elements that we're discussing. And so we're looking at, carbon, which we have there. We have our phosphorus, which we have there. There's our Catty Corner relationship. We then have our nitrogen, which is in the middle there. And then finally we have our oxygen, which is in the far right. So if we were to, maybe expand on that, this is what we are seeing over there. Right? So according to our trend, right, as far as size goes, we know that atomic size decreases in this manner. Right? So if we are to now, predict right the trend, right? We want the largest element, so we want the element furthest down and to the left in terms of predicting the trend as we have it, above. So that means we actually come into a problem here of that's two of them. Right? Carbon is the furthest left, but phosphorus is the furthest down. So that's the Kitty Corner or Catty Corner effect. So And so, in terms of that Catty Corner effect, I don't know why I keep saying that because I always call it Catty. Catty Corner effect. Vertical always wins. So that means in looking at our two elements, carbon and phosphorus, right, it's the phosphorus that's going to win. So that's just something that you might ask when you're approaching these types of questions. But really, especially with atomic size, you're coming down one whole level, right? So I mean, carbon's in that second principal quantum level, phosphorus is in the third quantum level, right? So again, you're adding all those extra atomic shells, or electronic shells, to the element, and that makes it bigger as well. But sometimes students have that problem with the left and down issue when you come across this type of Catty Corner relationship. Cations. Remember, cations are positively charged atoms. Right, these are always smaller than their neutral counterpart. And that's because now we have an excess of protons because we are positively charged. So if we're comparing, an example of, magnesium versus a magnesium plus 2, right? My cation is always going to be smaller. My neutral is always going to be bigger in terms of that regard. So that's cations. Anions are just the exact opposite. Right, these are negatively charged atoms. And they are always larger than their neutral counterpart. Right, because, for the opposite reason, because now we have an excess of electrons. A larger surface area, helps, lessen the electron repulsions. So that's the idea with anions. If we looked at an example of, bromine versus bromide, right, this is going to be bigger because it's the anion, and so here we'll have much smaller, which is that neutral element. So, comparing, charges, it's just a question of whether it's positive or negative. If it's positive, the cation's always smaller than the neutral counterpart. If it's negative, then it's always larger than the neutral counterpart. But what about isoelectronics? These are elements that are different, but have the same number of electrons. So, for instance, if we were to look at the periodic table, and if we were to look at, fluorine -1 and neon, these are both isoelectronic. Fluorine is here, and the neon is there. If we look at neon, right, neon has 10 electrons. If we look at fluorine, well, it has 9 electrons. Plus 1 electron because it's negative. So we have 10 electrons as well. So because of that idea of having them both having those 10 electrons is that notion of isoelectronic. So what about them? They have the same number of electrons. So they're different elements, but yet they have the same number of electrons. That means on the periodic table, we can kind of put them at the same kind of location if we're just considering electrons. So for isoelectronics, the element with the most protons will be the smallest. And counter to that, the one with the fewest will be the largest. So let's look at an example of this. We have sulfur -2 sulfide. We have chloride. We have potassium. And we have calcium +2. If we go to our periodic table, we find that all of these have the exact same number of electrons. If we look at sulfur, sulfur has its 16 electrons, right? Plus its 2 electrons because it's negative. So we have a total of 18 electrons, which is like argon, right? Argon has 18 electrons. And we find the same thing is going to happen with these other elements as well, right? In terms of, the chlorine, we can say, the same thing. Chlorine has 17. It has 1 electron because of the negative. But we end up with the same count. And we find the same works for the other ones as well, as far as maybe looking at our potassium +1. It's losing electrons now. So we have our potassium with its 19 electrons, now -1 because it's positive. Again, we get our 18. And then lastly, we have our magnesium. Oh, I apologize. Our calcium is right here. And so our calcium +2 would have the 20 minus then 2 electrons because of its positive charge. But we end up, again, the same. So basically that's saying that, our sulfide, chloride, potassium +1, and calcium +2 are all isoelectronic. With argon. So when we pick out size, we want to pick out what is going to have the largest number of protons. So in terms of this, trend, which I didn't really ask what I wanted as far as larger or smaller, but let's just look at the trend that we see here. If we look at, counting things up, we have, in all cases, 18 electrons, but here we have, with our sulfur, we have 16 protons, 17 protons for the chlorine, 19 protons for the potassium, and 20 protons for the calcium. Right? They all have 18 electrons because they're all isoelectronic. So that means that our sulfide is the largest because it has the fewest number of protons, while then our calcium is the smallest. And it has the largest number of protons. So that's the trend as we see it with isoelectronics. You have more protons, you have the same number of electrons in all cases, but more protons means, well, there's a greater positive core. They're holding onto those electrons tighter, and they're also holding onto them closer. So that's atomic size.